on local detection of Rydberg atoms.
Yeah. Thanks everybody for staying late on Friday afternoon. This is just kind of a tentative style. I will talk about this as well, but mainly I have no big results to report, but I want to report a few observations that are maybe of interest here to the community. And all this work was done in close collaboration with Misha. So what I will like to tell you about is our efforts to do non-local ensemble readout as a way of quickly measuring Rydberg atoms, because we know that's one of the problems in quantum error correction is this fast readout to implement it in the feedback loop. And then I would like to tell you a little bit about some things that we are thinking further ahead, towards the future. We are, many of us are very optimistic that we will have local quantum error correction in modules happening. It's already starting to happen, but that will have, working below threshold, real-time, mid-circuit readout, error correction going soon. And then one can ask, can we scale beyond the sizes that we can place into a single tweezer array? And I would like to share my thoughts on that. And then I'll tell you a little bit about progress towards integrating cavity QED systems and the Rydberg platform in our labs, and why we want to do it and why we think it's exciting. So for speeding up readout, as we know and as we have seen, in most cases, state readout is either slow or destructive or both. The best results in terms of speed, I think, were the results on the 20 microsecond, readout on the blue transition in terbium, which is, a beautiful result, but it also, that was a destructive readout. And then the non-destructive readout typically takes milliseconds to many milliseconds, which is not favorable for any mid-circuit feedback loops. It's maybe tolerable, but certainly not great, because it will, be one of the components setting the overall calculation or the overall cycle time of quantum computers. So one can ask then, how do we do fast? What are other ways to do fast mid-circuit readout? I would like, we have been exploring this fast non-destructive collective readout, where the basic idea is that instead of, why is the readout slow? Well, if you have one atom and you collect fluorescence with, typically maybe 1% or so overall collection efficiency, you have just the finite scattering rate by the atom given by the line width of the transition, and that sets this millisecond scale for most atoms. And here the idea is, because the Rydberg interaction is such a large range, you can in principle use a single Rydberg atom to turn on and off the absorption or scattering by hundreds or thousands of atoms, and then you get an enhancement factor in speed simply by the atom number. And so this is an experiment that we did now, I think, about 2 years back. So the idea is that we have a Rydberg state here, R prime, that we would like to detect. For us, it's a P state here. And in order to set up this collective detection, we use an ensemble of atoms, hundreds or thousands of atoms, and we set it up in such a way so the atoms are in the ground state that we have so-called Rydberg EIT. We basically have a probe laser. This is the 5P state of rubidium that we shine through the cloud in the presence of a control laser. And if the atom is not there in the Rydberg state, then you have Rydberg EIT. You have strong nonlinearities in the system, but here we are just interested in measuring transmission. So basically, if this state is empty, we have transmission through the ensemble. However, if this state is filled by even one atom inside the ensemble, then what happens, of course, the van der Waals interaction shifts away the Rydberg state out of resonance, and because this EIT line width is adjustable and can be relatively small, even a relatively modest shift is enough to now make the ensemble absorptive, and then you can collect, for instance, the transmission through the ensemble. And it's sensitive to a single atom. And so this is the basic idea. And let's just see, too many things to click through. But in short, we measure the transmission and plot the photon histograms through the ensemble. We can either not prepare an atom in this Rydberg prime state, and we see some photon number, some photon count rate, in this case, for instance, 40 photons. This was taken in just 6 microseconds. And then in the presence of a Rydberg atom, we see a shifted, much lower transmission on a little bit less average than 20 photon counts detected. These histograms are very clearly separated. However, you see here some tail. in the distributions, but at this point this was about 92 or so % fidelity of detection in just 6 microseconds. This is for rubidium, so this is not the terbium of one of these relatively broad transitions. This is for rubidium with just a 6 MHz line width, where typically detection takes several milliseconds. And this was also not using a very good lens. The NA of this lens was quite low, so one could do better than that. So yeah, we had 92%, and we could also show that it's non-destructive. We can basically do 2 measurements. We can detect the counts in the first 6 microseconds and the counts in the second 6 microseconds, and you see that they align more or less along the diagonal, which means that your first measurement, if you measured no Rydberg atom in the first measurement, you will also measure no Rydberg atom in the second measurement, and vice versa. So it's a non-destructive measurement of the Rydberg state that can be repeated. We also saw that we could prepare in the cloud very nicely a single atom, again by Rydberg blockade, and that we drove within the cloud with microwaves a transition between 91p3 halves, where we prepare, and say 92s1 half. We see these nice Rabi oscillations between the Rydberg states. So this means just that coherence properties of the Rydberg level are actually not affected, even though we have it in a sided ensemble of a few hundred atoms that are otherwise in the ground state. And then the detection of this is just done by this collective and very fast method. So it's potentially also an interesting system to prepare, instead of a single Rydberg atom, prepare a single Rydberg atom in an ensemble with reasonable coherence time, which has the advantage that no sorting, for instance, is necessary. Just prepare the ensemble, and then within a few microseconds we can make a single Rydberg atom, and then we can read it out on the same time scale of a few microseconds. What limited our fidelity? Why didn't we do better? And this is closely related to many things we have seen. I've been grilling Monica about their experiments. I think it's related. So basically what we see is that when we had no Rydberg atom, this is the orange curve, then more or less we have high transmission throughout with a little bit of a decay. The little bit of the decay is presumably preparation of a Rydberg atom from the Rydberg EIT, which gets stuck in the system, but that is not a big problem. The bigger problem is basically that when we have prepared the Rydberg atom, this gray curve, then the transmission slowly goes up, which means somehow this atom in the Rydberg p state disappears on a time scale which is much faster than the decay, and we measured this to depend on the control laser. So this is something we don't really fully understand. Maybe it's related to these avalanche processes where something is created and then pushes the Rydberg atom out. But basically what we see is that when we have a higher control Rabi frequency, then our available measurement time is shorter. And this process was limiting the fidelity of the systems. And you can kind of see it here. It's basically you start out with a Rydberg atom with flow transmission, and then you create some background here with some probability of apparently this Rydberg atom disappearing and not leading to blockade. This is something that we would like to understand a little bit better. However, this is basically preparing a Rydberg atom inside the ensemble. If you really wanted to use this as a detector in any general single atom array experiment, one geometry that you could imagine is you could have your single atom array for quantum computation, and then somewhere a region with small ensembles where you bring the Rydberg atom close via transport in the tweezer, and then you can try to see whether you can non-locally detect this Rydberg atom, not by measuring its fluorescence, but the transmission through a small ensemble. So for this, we set up arrays of small ensembles. These are made with spatial light modulators in different patterns. So these are atoms, but these are not single atoms. These are on the order of between tens and hundreds of atoms in each ensemble. We achieve this simply by making the tweezers a little bit bigger, between 2 and 3 microns, and changing the parameters. So when on the certain parameters, we load single atoms, but on the other parameters, we can actually load many atoms in this system. So these are the ensembles, and traps are just slightly bigger than single atom traps, 2 to 3 micrometers. And so then we can ask ourselves, can we do the same thing? Can we basically have a non-local detection where a Rydberg atom outside the cloud but near the cloud can turn on and off the absorption there? And we have been working on this. We have this 1D set up now, detect control configuration. And so basically what we can do is we have a preparation beam where we prepare a p state via 3 photon transition, 2 optical photons and 1 microwave photons in the middle ensemble. And then we can look at the EI3 transmission through the middle ensemble or also through the ensembles nearby. And I would say at the moment the results are modest. If we prepare right inside the ensemble, we have something like 70, maybe 80% fidelity of detection of the Rydberg atom, as shown by these blue and orange histograms. And then you can see that there is an effect in the nearby ensemble, particularly on this side, but the fidelity at the moment is not very good. This distance, I forget now, it's on the order of, I think, 10 micrometers or so. So basically, this is still detecting an atom, a Rydberg atom that is about 10 micrometers away from the ensemble. So the Rydberg atom is prepared here, and then we are measuring transmission through the left ensemble over there. So we are trying to understand things better, and of course, this is only really interesting if it can be pushed, I think, to the 99% level or so, but it is on the microsecond scale for rubidium, which may be interesting for many experiments, and it wouldn't be a very complicated thing to add to existing setups, just a few more traps in some region that are a little bit bigger. So this is the best non-local detection fidelity so far. Is this histogram close to 80% fidelity, but this is work in progress. And we are trying to understand what limits us. We see, among other things, much larger Rydberg state line width than we expect. So let me switch topics and then I come a little bit back to the setup. So the other thing is kind of thinking ahead. Let's say that we have soon logical qubits with local error correction mid-circuit that are working below the surface code threshold, for instance, or some other code threshold, so that we have local quantum error correction. And then one can make arguments, and many of us believe that these will be rather large systems in terms of physical qubits. I think 1,000 is already where we are now, right? And it will be probably 10 to 100,000. If you have 100,000 traps at 1 milliwatt per trap, you need a 100-watt laser. So that will probably be a somewhat hard limit on the number of physical qubits. The other somewhat hard limit, which maybe can be solved with money, is the field of view of the microscope, right? At the 3-micron spacing and the millimeter square field of view, you can also fit 100,000 atoms. But they're kind of two limits more or less coinciding at, I would say, 10 to the 5 physical qubits. Misha likes to point out that when they make, chips, they have, inch or I don't know how many inch size wafers. 6 inch size wafers, so it could, you could imagine somehow to pay, $5 million or however much these lenses cost to make something bigger. So maybe the field of view, 500 million, okay. I see you looked into it already.
No idea.
Our current funding is not yet there. Maybe the field of view can be solved with money, but the laser and heating thing is so there's probably a hard limit, and so we'll have as a field to think beyond that, And the most natural way to think is in terms of modules. We have these modules of, say, 100,000 physical qubits. Is there a way now to make an even larger system by truly quantum connections and not some classical connections? And what will be needed? And so we looked particularly into a way, which has been around as an idea in the community, which is to make bell pairs between, say, two modules and then weave them in via local quantum error correction. And we think that's a good approach. Somehow my slides are out of, I'll come back to this. This is the picture here. So we imagine, for instance, a surface code, consisting of modules where local quantum error correction is running. And then the idea is that if we can make remote bell pairs by methods that have been investigated by the community, by particular optical methods of making non-local bell pairs, then one could, basically weave these into the system and make either non-locally stored logical qubits or implement quantum gates between distant qubits once these bell pairs have been weaved in. And so what you would do is basically you would distribute a bell pair between these two modules, and then you would, with logical error correction, fit it into this side and this and the other module, and then basically establish a true quantum connection between them. And so you can ask yourself, how good do the bell pairs need to be? And in the literature, there were ideas that the quality of these bell pairs doesn't need to be very good. I mean, the bulk error threshold in surface code is 1%, as we know, but there were indications that maybe 10% errors could be tolerated. This had been done either in the limit of very small systems, with 3-qubit nodes where things are not quite as good, or when you looked at asymptotically, if you assume you're kind of at bulk error almost 0, you can also show that you can tolerate 10% Bell errors. So we did a more serious calculation of reasonable sizes, and so what you see here on this axis is the physical qubit bulk error, and this is the logical qubit error on the vertical axis. This is the bulk threshold for the surface code at 1%, and then what is shown is basically different sizes of physical qubit arrays. L equals 3 is a 3 by 3 array, where 9 physical qubits constitute a logical qubit, and this would be, for instance, an 11 by 11, 121 atom array. And then we looked at what quality of Bell pairs do you need. And so in this plot, we assume the 10% quality of Bell pairs. So we assume that you can make in a heralded way, let's say Bell pairs non-locally, but which have only 90% fidelity. And so previous systems had looked at, for instance, distillation, but this is not very efficient. This is direct. We're just using the Bell pairs directly, no distillation necessary, and they have 10% error. And what you can see is that the threshold moved just a little bit, but more importantly, the asymptotic behavior, once we're down here, is basically indistinguishable from bulk error rate. So a 10% Bell pair error will cost you nothing, essentially. So current experiments are somewhere around here, where there's still a bit of difference, but once we push towards this 99.9%, basically it will cost nothing to implement this Bell pairs, as long as you can make them with 90% or more, which has been demonstrated in experiments. And then basically the main challenge is how to generate Bell pairs at a sufficiently large rate in the system. And so here people have explored free space approaches. Free space approaches are possible, but are relatively slow. The coincidence rates of photons are very small. So a very natural way is to use cavities. You could use these cavities in 2 different ways. You could use either local cavities and use them just as efficient ways of collecting photons. If you have a cooperativity of 1 in the cavity, that's equivalent to collecting all photons into 4 pi of a system, so much better than normal numerical aperture lenses. And you could also, however, imagine that you had, maybe different modules all within one vacuum chamber at some smaller spacing, with multiple microscope objectives, in which case you could just put a single cavity into the system, and then you would have a very highly efficient Bell state preparation, because within the cavity you can do this much better. So this is one of our interests in cavities. The other of our interests in cavities is that we're all working towards faster detection, but free space detection that does not affect the memory qubits has yet to be demonstrated. You need beams to scatter light at a consistent rate. If the beams are Gaussian, very small, maybe you can do that, but the cavity seems very natural, because you really need only a single photon inside the cavity at any time to detect an atomic state inside the cavity. So it seems very natural to think of codes where, say, you have a surface code here, you move the ancilla qubits into the cavity, or maybe they are already into the cavity because you use 2 species like Hannes uses, and you make this talk to cesium and not to rubidium, and then you can try to do syndrome detection, try to do error correction. The one disadvantage of cavities is that they are serial in principle. So when you take a picture on a camera, you can measure many qubits at the same time, although camera readout rates are small. With a cavity, per mode, you can kind of measure 1 atom. However, in the limit where your ancillar errors are small, which is the limit where 1 to just a few atoms, you can actually make simple logarithmic scaling of the system. You can just look, is there an error in the whole system? If there isn't, you are done. If there is an error in the whole system, you can address the left half, the right half, etc. And so you can, in a logarithmic way, look for errors in the qubit system, which is not very complicated. And the readout is very easy and very fast, because this can be microseconds to 100 nanosecond time scale for readout. So this is something that is of interest to us as well, this kind of logarithmic scaling. Okay. Maybe now this is for the experimentalist. When we try to put in a high finesse cavity into our system, we got some very good mirrors from Monica that she has in one of her systems, and she saw also the cavity degrade. She tried to build a nearly concentric cavity, right? And it wasn't quite clear, but the finesse after baking was just worse, much worse. And unfortunately, we experienced the same thing. So here we have 3 different mirrors. They had 50 to 80,000 finesse mirrors. What you see is an AFM of the mirror surface. So nice, kind of this typical 2 angstrom or so RMS surface. And when we baked the system for the vacuum, finesse dropped precipitously to 15 to 20,000. We had in previous experiment been able to flood the chamber with oxygen and restore some of this finesse, but we weren't able to in this case. And when we looked with the AFM of the surface of the mirrors, it consisted of these extremely sharp spikes. So this is a zoom in. So basically something very bad happened to the mirror surface where there was some kind of growth out of the mirror surface above these temperatures with many, many spikes, which made the RMS roughness much, much worse. And when we tried to fix it in various ways, it just got worse. So the warning of this story is, so these mirrors consist of tantalum, maybe I have it somewhere here, consist of tantalum pentoxide and silicium dioxide layers. Typically, the coating companies like to put a tantalum pentoxide layer on top because it has high index of refraction, so it kind of saves them 1 layer or something in the number of layers. But actually, we know that tantalum pentoxide is very bad in this irreversible way. So what we think is happening is that first there's some kind of oxygen depletion, and this oxygen depletion in the layer makes somehow holes, make this porous, and then allows some kind of very sharp growth. So as a warning sign to all experimentalists, yes?
What kind of etch do you use? Is there like a selective etch?
Yeah, we basically tried to figure out what this growth is, and it's not silicium dioxide. And we figured, we did a selective etch to figure out what it was. And it's not also some deposition on the surface. It's something that grew out through these pores. It must be some self-assembly process of some sort. And there's some indication that people know about this in the solid state materials community. But maybe here's a warning sign, make sure that your top layer is SiO2 and not tantalum pentoxide if you're ever going to build cavities. Okay, so this is our system that we set up. So the old mirrors that we got from Monica would have allowed us to have a cooperativity of 10 or 20. We use now other mirrors that had a different top layer, which allow us to have a cooperativity of 2 or so. This is the setup that we have, 2 cavity mirrors, maybe 3 centimeters or so apart. Some A spheres inside the vacuum with quite high NA. This one is 0.55 NA to be able to image single atoms. And this is the real setup. As you see, it starts to look as if it was going into a cryogenic system, but it's not. It's just at room temperature, lots of wires, but basically this is one mirror holder. So we have just now 1 cavity. Originally we had 2 cavities. We have 1 cavity holder and then lenses from top and below. This is the system that we have right now. We can image the mode inside the vacuum chamber. This is by shining light into the cavity mode and then placing a mod inside it. So this is this bright thing that you see. So we can use this to align the atoms to the cavity mode. And this is an average of tweezers. And these are now single atom tweezers, actually. So we're just getting ready to place these single atoms in the tweezers in the cavity mode and start to measure, do state detection with them, etc. The cavity geometry is such that we should be able to place on the order of 50 to 100 qubits or physical qubits simultaneously into the cavity mode, or move it in and out if we like. And so some of the first things we would like to do is to demonstrate maybe this logarithmic search for an error in a larger system, as well as Bell state preparation. So maybe let's see. Let me go back. Maybe I have what's the time? I want to show you something curious that we observed in these ensembles. Let me go back. So basically, we were working with these ensembles and small tweezers on the order of 3 microns or so. And so what we did at some point is we said, okay, we would like to load as many atoms as possible. So we ran a machine learning algorithm that simply optimized the atom number It was quite nice. I mean, the students had tried for a few days and got some number of atoms in the machine learning within a few hours, got 6 times the atom number loaded into the tweezers. So, talking about making us superfluous, But we saw also something very weird. We saw this very dense region appearing in the tweezer, and this was just polarization gradient cooling. And so most of you are young here, but for those of us who are older enough to remember the history, it's a well-established belief, truth in the field that polarization gradient cooling cannot create Bose-Einstein condensates. However, we have this dense region, and if we do a time of flight with it, this is what it looks like. Okay, we have this very narrow peak that hardly expands at all. This is the time of flight. You see the thermal component in the 2 different directions, vertical and horizontal direction. So the thermal cloud expands isotropically at a temperature of about 30 to 40 microkelvin. And then notice this scale. This is the expansion of this little peak here, right? So this is hundreds of micrometers in the same time, and this is a few micrometers. So this is the horizontal expansion, where we see a little bit of energy. If you were to fit it with a thermal distribution, you would see a microkelvin or so compared to the 40 microkelvin of the real thermal cloud. And then in the vertical direction, we see no expansion at all. Again, for those of you from the early times of Bose-Einstein condensation, this anisotropic expansion, where the expansion is the slowest, where the vibration frequency is the lowest, is a well-known hallmark. And so it looks like our machine learning algorithm just created accidentally a BEC in the system. It's a few percent effect. The way, and I forgot to mention, this only worked because we hadn't aligned our trap very well on the microscope objective. So it was really displaced by a little bit, by a few degrees. If we align the trap very well on the microscope objective, we never see this. We just see a thermal cloud. So it requires some misalignment, and it also requires, it only works in a certain range of tweezer sizes. If we make the tweezer size very small, this extra condensate goes away, and when we make it large, say 5 microns or so, it also goes away. So it only works in a sweet range. And so the way we think what is happening is that basically this misalignment creates corrugations in the potential, and it has been known from Wolfgang Ketteler's work, where he put a dimple on purpose into such a Bose-Einstein condensate trap, that if you drop your dimple below the chemical potential of the gas, then and he could see even reversible condensation in this system, basically. And we think that this is what is going on. If you measure, for instance, the fraction of atoms in this small cloud, we see up to 5%. That also scales with the phase space density of the thermal cloud. So the more closer to the threshold the thermal cloud is, the more atoms we see in this little condensate. We don't really know what the local potential looks like, but people tell us that if you misalign things, Markus Greiner tells us that if you misalign things on microscope objectives, that the potentials look very bad. But you would need a very small structures in this, near the minimum limit. Depending on how we align things, we see sometimes, the original one I showed you was a nicely symmetric one here. That's the first one we saw, but depending on alignment, we can get this little dimple be somewhere on the side, sometimes even have 2 little dimples. So this all makes us believe these are local corrugations that drop far enough below the chemical potential to have a formation of a Bose-Einstein condensate. As surprised as we were by this, because as I said, it has been a long established truth that it's basically not possible.
Vladan, you said initially when you align everything, it's about 200 to 500 atoms, and then with the machine learning algorithm and this alignment is 2500 atoms?
So the whole cloud without machine learning, we didn't see it, presumably because we had too few atoms. So without machine learning, we had about 500 atoms in this 3 micron trap. After machine learning, we had 2,500 to 3,000 atoms. And that's when we saw this. So this is maybe 3,000 atoms in the system. And the peak contains maybe 5% of that maximum. It's very simple, yeah. We just do a mod, and the only thing we did for the machine learning is we said you have 40 milliseconds during which you can switch the magnetic fields, the magnetic gradient, the detunings of the lasers, and the powers of the lasers, the mod and the repumper. And you can choose the times. You gave it free, it could choose how long it does that. So in 40 milliseconds, it just does some cooling, nothing very remarkable, things that we know. It ramps up the gradient, it turns down the repumper, it jumps the mod laser far off resonance, kind of the things you would do anyway. It does it maybe a little bit more suddenly than a human would do it, but it definitely loads more atoms. And even, our cost function wasn't something complicated, like make the highest phase space density optical depth. It was just maximize the atom number loaded. And it's pretty remarkable. I mean, in 3 micron trap, according to Mark Suffman's paper, I think you can make a single atom preparing it, right? But you can also make 3,000 atoms prepared in pretty much the very same trap, depending on your laser cooling parameters, which I found interesting. But this is what it was really an accident. We didn't plan to do this, but it's maybe interesting to see. Sorry?
How cold is the cloud?
The cloud is about 30 microkelvin, the thermal cloud. It's very, very hot. Right. And then you have to assume that the volume of this dimple, right, in a simple model where it's a square, is about 10 to minus 3 of the whole volume of the trap, which maybe is not... Sorry? It has to be very deep as well. So, interference can make it in principle very deep. It has to be about a few megahertz deep. So the whole trap is a few megahertz deep, maybe 3 to 6 megahertz, and it has to be another 3 megahertz or so, 2 to 3 megahertz deeper, and much smaller.
Are you surprised that no one did this before? I mean, I could construct a trap like that easily on purpose and just put it...
Yeah, I mean, in the end, what we also did is we, instead of using misaligned tweezers, we made 2 tweezer trap well aligned and brought them together. We saw the same effect. But it only works in a sweet range of potentials.
I mean, this end of this results. I mean, he always claims it's laser cooling to PC, but probably it's a different. No, I think
It's different.
It's more understanding.
Yes, I mean, in Florian's work, the main idea is that you have a dimple like that, but you mainly use it to tune your narrow line cooling out of resonance, so that the atoms in the dimple don't see that, presumably the cooling laser, and it cools only outside. But, it works with rubidium, that's all I can tell you. After we knew this, we tried different geometries, and in many of those, we could recover this effect without being able to be very quantitative. I don't have pictures here, but we have also pictures where we put 2 traps. If we place them far apart and they're well aligned, no such BEC, but when we put them close together so that there's interference between them, we see a BEC form with polarization gradient cooling, but it only works also, the trap size is pretty critical. With 5 micron traps, we never saw this, for instance. So you have to be kind of in a sweet range.
So it's rubidium, right?
Yeah, this is rubidium.
Yeah, I see. That's just thermalized.
So what is the actual size of this BEC region, the red circle?
So this is at our resolution limit, so it's probably 1 to 2 microns, I want to say. Let's see here. It's actually, if we look at this, maybe 3 microns or so is the size of this region, and then the cloud is larger, maybe 10, 20 microns or so. Okay, so it's kind of a strange and interesting thing, but maybe to keep in mind for future. And it's very, very fast. It's 40 milliseconds. Okay, nothing. It's really what we consider the trap loading stage in a normal experiment. Okay, and then maybe just as a final thing, sorry, I want to click all through all this. Okay, so maybe one last thought here is the following, and I know some of you have been thinking about this, but is it not showing? Okay, all right. Okay, so maybe one last thought about this, and talk to Jeff. He had some ideas. So one of the other problems that we need to solve in the field, I think, is some kind of continuous reloading, because we know that the gates lead to loss. It's a small percent of loss, small percentage, but there will be many quantum gates. We know that detection at the moment at least leads to loss and so on. So we need to think about how to do, continuous cooling or continuous replenishment of a reservoir. So this is one of the ideas that we want to try for this region, for another region, which maybe could be look as the following. You could have a mod off-site, maybe a few centimeters away, somehow isolated with some nice baffle so that the fluorescence doesn't do very much. And then people have shown quite long-range transport. For instance, Dieter Mesched and other groups have shown quite long-range transport in moving optical lattices. And for instance, Shimon Kolkowitz has also shown nicely that you can use a moving lattice to pull atoms out of a magneto-optical trap. So you could imagine a system, and we're looking into this, where you have a moving lattice which somehow extract atoms from a MOT. Then maybe you have one microscope here, some kind of atom detection region. That could be a cavity, could be a microscope that tells you which of these lattice sites are filled with an atom. And then you could use this information in some other region, tweezer pickup region, where you could then kind of just blindly take a tweezer and maybe deliver the atoms to some storage region. So basically the thing that I'm trying to accomplish is to be able to run a computation, a simulation sequence here, while continuously replenishing the system. And right now, the way we do it, of course, when we have resonant light in the region of replenishment, then certainly all coherence is lost. So this might be one way to make effectively a slow beam deterministically of delivering atoms. But if you have other ideas, I would really be very interested to discuss, because I think this is one of the other burning, kind of maybe silly technical problems, but that could make or break this effort. And with this, I would like to thank you for your attention.
For the chemical readout, on a technical level, is there any difference from what Dan standard did already?
No, I mean, people have now for a decade detected atoms.
He did non-destructive.
He did non-destructive, right? So the only thing is, I think you want to do it with being able to put arrays in there, move atoms in and out, and so on. Yeah. Yeah.
Atoms in and out.
Right. So for instance, we would like to show that one can run Rydberg gates next to the cavity and read the atoms out through the cavity and not touch, any coherences in the atoms, things like that. Yes.
Yeah, so your microwave manipulation of the SMP states showed actually very long coherence time. Is it not affected by atom number fluctuations?
No, this is a single atom prepared.
This is
So we use, this is just a single atom so it's in the blockade regime.
Yeah.
You would expect to prepare a decay state, but the decay coherence time is super short, 100 nanoseconds or so. You're preparing just randomly somewhere in the ensemble one single atom.
Okay.
And all that you see here is a single atom Rabi flopping inside the ensemble. So it's one of the atoms in the Rydberg state.
I'm wondering for this error detection with these syndrome measurements, you mentioned this sort of binary search that kind of essentially lets you efficiently do the local measurement. But I'm wondering if you were to rethink how to design the error correction with the fact in mind that you're naturally doing these non-local measurements, whether you would do anything.
I think there's a lot of room for improvement, I think, to think about how to do it. I mean, of course, you can also do atom number resolving measurements with this cavity pretty easily. So you could, maybe first detect the number of errors that you have before you start searching for them, and maybe there are more clever ways to do it as well. I would just like to point out, with the cavity, 1 microsecond or even 100 nanosecond readout is not hard, right? So that's a big factor potentially.
For connecting modules, what kind of entanglement generation rates are you thinking you need?
We think that you need, it depends on the size and on the loss rate, but I think you need something like maybe 10 kilohertz of bell pairs, and which is within reach with optical method if you use, for instance, cavities or very good. Free space is maybe lower, but something.
Like in theory is possible, but in principle, the rates that people have achieved are order 10 hertz?
The rates people have achieved in free space, maybe 10 hertz, Chris Monroe or something like that.
Like
Yes,
100
there are kilohertz rates now, but they're mostly ions or some other
Yeah.
like non-neutral atoms.
Isn't Lucas group 180 hertz or something?
It's 180 or so.
Yeah.
But there is a result from not Lucas's group, but there is kilohertz rates.
Yeah, with ions and traps. For ions, I didn't point this out, but for ions, this is much more burning, right? Because they are stuck to, unless they really move the ions very well around, they are stuck to 50 or 100 ions, not 100,000. But
But this methods become much more powerful for bigger systems.
Exactly,
That's
right. That's the main point. I didn't show that. Basically, it's not as good if you have very small systems. It's actually better the bigger your module is. Because it's basically edge length that matters, whereas the number of physical qubits is the whole volume.
Aziza wanted to
I literally wanted to ask that.
Gotcha.
For this ensemble readout, do you see, like, you mentioned that maybe some, like, the fidelity of readout might be limited by these, like P atoms, like, disappearing or something like that. So do you observe then, like, dependence of fidelity on the number of atoms in this, like, single ensemble? Like, at a lower density, in principle, that should be, like, less of a problem.
That's true, I think. The reason is why so basically the enhancement in speed is given by the atom number at best, right? If you do the best thing, so we would like to have hundreds of atoms if we want to go to, say, sub 10 microsecond readout. But yes, it scales with density. I think it's a problem that's solvable. One has to just figure out what the exact mechanism is. And the idea is that if it's some Rydberg decay or something else, if you couple that level that is disturbing you to some quickly decaying state to the ground state via another laser beam, it should be fixable. But this is a problem that plagues many experiments, right? These avalanches.
Microwave gravity, for example.
Maybe that would work too, but we need to understand the mechanism.
So maybe only quick question.
And also off of that, does it also scale with distance because of the van der Waals shift?
Probably, but we haven't measured that. All right.
All right, let's thank Vladan.